All right, welcome everybody. Today, this is Dr. De La Corte's class, Physics 106, and today we're going to be talking about the relationship between force and field. To begin, we'll talk about what we know occurs with interactions between charges. We know if we have a positive and a negative charge, as seen at the top, these two will attract. While we know that if we have two positive forces or two negative forces, these will repel each other. The strength at which they repel each other, or the interaction between them, is what we call the force. This brings us to our first equation. We're going to talk about a few equations today. The force equation equals K1 times K times Q1 Q2 over R squared. Let's break this down a little. We know that Q is the charge, R is our radius, but K is our constant. K equals 8.99 times 10 to the 9th. And then the units on this are really important. Newtons times meters squared over coulombs squared. And you may ask yourself, why do we have those units? Well, in our equation, Q is our charge, which is coulombs squared, and R is our radius, which is meters squared. And in order to complete this equation and end up with a force, we need these units to cancel our units. So the meters squared will cancel, and the charge will cancel, and we end up with newtons for our force. So let's talk a little bit about this here. If we have multiple charges rather than fewer charges, our force will increase and our charge will increase. If we decrease the radius between two charges, the force increases, and obviously we said the radius decreases. If we increase the radius between two charges, the force decreases, and you can determine that from just the simple equation. Let's come to our first practice. A point charge has a magnitude of 3 times 10 to the negative 6 coulombs. A second charge has a magnitude of negative 1.5 times 10 to the negative 6 coulombs and is located 0.12 meters away from the first charge. Determine the force the charges exert on each other. So first, we will write our equation. And then let's write what we know. Our Q1 is 3.0 times 10 to the negative 6th coulombs. Q2 is negative 1.5 times 10 to the negative 6th coulombs. And our radius is 0.12 meters. And we're going to square that in our equation. So let's take time to write this all out. Force equals K, which is our constant. Multiplied by Q1, which we said was 3.0, times 10 to the negative 6 coulombs, times Q2, which was negative 1.5 times 10 to the negative 6 coulombs. And that's all over our radius, which is 0.12 meters squared. If we punch that into our calculator, we end up with 2.78 newtons. And remember, we get newtons because all of the rest of our units cancel. Good. Let's move on to the electric field. If we know that if we have a positive charge, it exerts force, has an electric field in all directions, as shown here. If we insert a point charge, this little guy here, it has a certain charge, And this field exerts a certain force on that charge. So let's look at another equation. E equals K Q over R squared. So just like the last one, this is the charge of our point charge and the radius between it and the electric field, the origination of the electric field. And so to come over here and look at another equation, what magnitude point charge creates a 10,000 Newton per Coulomb electric field at a distance of 0.259 meters? Well, first we'll write our equation. E equals KQ over R squared. We know our force, or our electric field, excuse me, is 10,000 newtons per coulomb. And our radius is stated in the problem as 0.259 meters. Square that again in our problem. So to write this out, to solve, E, 10,000 newtons per coulomb, equals K, which is our constant that we've talked about. And then we'll multiply that by the charge, which we're trying to determine from this problem, over R squared. Let's try that again. 0.259 meters squared. Now, if we punch that into our calculator, we'll be able to determine the charge, which is 7.5 times 10 to the negative 8th, and the charge is always in coulombs. And then we come to part B, and they ask us how large is the field at 10.6 meters. Well, we know the only thing that changes in this problem, now that we know our charge, is the radius. So let's punch this in again. E, which we're trying to determine, equals 8.99 times 10 to the 9th multiplied by the charge we found, over the new radius, stated here, 10.6 meters squared. Now our field will be in newtons per coulomb, and if we punch this into our calculator, we find that it is 0.6 newtons per coulomb. Let's come to the practical application here. Our relationship between force and field, our force here equals the charge times the electric field. Or we can say the electric field is the force over divided by the charge. And our application in field lines, for example, if we know that this charge here exerts an electric field of 5 newtons per coulomb, and this point charge is 0.5 coulombs, for example, we can use this equation here, F equals QE, or E equals F over Q, to determine the force between these two. For example, this one, the force times the charge multiplied by the electric field, and that would give us a force of 2.5 newtons. So this is really practical, and we can use this in field lines, especially when we know the electric field, or we know the charge, or if we know the force, and we can determine all of this information in this problem. So let's take a look at one more practice problem here. Determine the force on a small charge of 6.0 nanocoulombs and an electric field of 3 newtons per coulomb. we will use this equation we just learned. Q, we've determined from this equation, is 6.0 times 10 to the negative 9th coulombs. And our force is stated in the problem as 3.0 newtons per coulomb. So to write out the equation, F equals QE, or if we are determining the electric field from this equation, we're determining the force from this equation, we will write it out as F equals Q, which we know to be 6.0 times 10 to the negative 9th coulombs, multiplied by the electric field, which is 3 newtons per coulomb. And we'll find our force to be 1.8 times 10 to the negative 8th. And that's always in newtons. And so hopefully this helps you understand the relationship between force and field. Although they are very similar, they're not exactly the same thing, and they can be derived by this equation.